Welcome everyone to this webinar organized by the 5G-SMART project on the interesting topic of 5G for smart manufacturing, industry and 3GPP latest status. My name is Leefke Grosjean. I'm the project coordinator of the 5G-SMART project, working for Ericsson Research in Sweden. I'm here together with my colleague Christian Hoymann, also from Ericsson Research, located in Germany. Christian is a research leader who has been around for a while now, driving the evolution of the current and next generation radio access, and he's head of Ericsson's 3GPP RAN delegation, and therefore the absolute right person to give us the latest status from 3GPP. The second key speaker in this webinar is Krister Landernäs from ABB Corporate Research in Sweden, and he's a principal scientist in the area of wireless communication. And having been active in standardization himself, I think we get the perfect link from standardization to smart manufacturing. Furthermore, he's the technical coordinator of the 5G-SMART project. Looking at the participant list, I can see that we have a great community, and so welcome everyone on board. Before actually starting, I will quickly walk you through a couple of things to take note of. First of all, this meeting is recorded. This includes questions and answers both at the end of the session, but also during the meeting. Second, we are happy to have an interactive webinar and therefore encourage you to ask questions directly when they pop up in your head so that we can answer them right away. But there is, of course, also time reserved in the end of all presentations for a question and answer session. You can ask your questions directly by unmuting yourself, or you can use the chat function, and I will try to keep track of the questions in the chat. Should there be any unanswered question at the end of the meeting, we will get back to you with an answer via email. But in order to allow for everyone to raise their voice, we do, however, need a bit of discipline, and therefore ask you to make sure that you're muted while you are not talking. It seems to work very well right now. All the material shown here, that is slides and recording, will be made available at our website and our social media channels. Now we're ready to take a look at the agenda. After the short introduction happening right now, I will give you a very brief overview of the 5G-SMART project so that you understand how the idea of producing this webinar was triggered. After that, Krister Landernäs will take over and talk about the journey we have entered towards smart factories with 5G. 20 minutes reserved for that. After that, we will pass on to Christian Hoymann, who will give us the 3GPP RAN perspective on 5G for manufacturing. And here we have 40 minutes. And as I already said, we will have some room left in the end of the webinar for additional questions, answers, and discussions. So then let's get started with the first presentation by me, explaining you in a few words what the 5G-SMART project is about. So 5G-SMART is a European project that started in June 2019 and is running until the end of 2021. And the acronym 5G-SMART stands for 5G for smart manufacturing. 5G-SMART efforts span over the entire width, starting from the integration of 5G into this manufacturing ecosystem to actual field trials and further to research questions on how to enhance 5G for smart manufacturing. And the work on integration of 5G in the manufacturing ecosystem looks into business models emerging from having 5G available. We're doing a business impact analysis together with our OT partners. We've put quite some efforts into the analysis of new vertical use cases. And finally, we are investigating and evaluating different deployment options also for smart factories. Our field trials here in the middle aim at demonstrating, evaluating, and validating 5G capabilities, and we have 3 of them. So these sites are in Ericsson Smart Factory in Kista, where Ericsson together with ABB looks into 5G for enhanced industrial robotics applications. Then we have the IPT Fraunhofer shop floor in Aachen, where we're looking into 5G for enhanced industrial manufacturing processes. And then finally, a Bosch factory in Reutling, a semiconductor factory, where the focus is on 5G for enhanced semiconductor factory automation. And this is also the site where we have a measurement campaign, which is actually ongoing right now, performing channel measurements in the semiconductor factory, as well as electromagnetic compatibility tests. But 5G-SMART has the ambition to also go beyond the trials, which are in terms of 5G based on Release 15 products. We do also have research-oriented work streams dealing with how to enhance 5G for smart manufacturing. And here we study and propose new 5G features, network architectures, work on improving inter-cloud coordination, and an industrial-centric framework for network management and configuration. All of these new features with the target of smart manufacturing in mind. Below here, you can see the consortium of the project, and we're happy to have collected key players from the telecommunications industry, vertical industry, device vendors, and the research community in the consortium to make a powerful impact. Having a diverse consortium, we quickly noticed in the project that there is a great deal of learning and information exchange between the different domains of expertise. And the discussion topic that frequently came up is to better understand the link between the vertical industry needs, requirements, constraints, with the work done in 3GPP on 5G standardization. And with this topic being of high interest within the consortium, we felt like that it is relevant for a wider audience working in this intersection as well, and therefore decided to set up this webinar. So this is my introduction. Almost all from my side, but before actually handing over to Krister, I would like to take the chance to already announce our next webinar, which is on the 13th of October, 2 to 4 o'clock. And this time we will look deeper into one of our trials, the one in Aachen. And in this webinar, we will go deeper into 5G process monitoring and manufacturing. And there will be 2 live demos. So this is definitely worth signing up for already now. And you can find the link on our webpage to sign up. And I will also post the link for signing up in the chat window here. Okay, now let's get started. I will hand over to Krister Landernäs now. Krister, are you ready?
I am ready. So
great.
Let me just share my screen. Let's see if we do like this, perhaps. Just let me know, Leefke, if it's something is showing up.
Yes, I can see something.
You can see it before me. Good. So hello everyone. Also warm welcome from my side. As Leefke already told you, I will talk a little bit about 5G in the context of smart manufacturing. I will discuss a little bit about the potential that we see with the technology, the benefits that we see in industry in general, and then also more specifically targeting manufacturing. I want to start out with maybe looking at the big picture and a little bit about the history. So we've had over the years a number of evolutions, industrial evolutions, going back from sort of the mechanical to the electrical mechanical evolution, and then we had the software evolution, and now we're in the middle of this industrial 4.0 or digitalization evolution that is currently going on in our industry. And you have similar evolutions or generation also in the cellular industry with 2G and 3G and 4G and now 5G. Now what makes this, at least in my mind, a little bit interesting is the fact that we have both 5G and Industry 4.0 at the same time. So changes both for ICT companies and OT companies that are bringing together, well, basically projects like this and other collaborations that we haven't had in the past. So it's a really interesting time for both industry and ICT. In this presentation, I will focus on what you see here in the middle, so the industry or the fourth industrial revolution. However, there are large changes also happening in the energy domain and in the transport and infrastructure domain, where 5G also has a key role to play. So many of the things that we discuss here today are also relevant in other domains outside our industry. A little bit about then the potential and why are we interested in 5G. Let me just make it clear that, I mean, ABB, we do not develop 5G technology. We did, however, at one point in time, we did develop a car phone in the 60s. So I mean, things could have been different, but currently we don't do any 5G development. We trust that companies like Ericsson and Orange and others, they do this development. However, we see the technology as an enabling technology, enabling new applications for us, and therefore we try to influence the development of the technology so that it also fits the industrial applications that we provide. A couple of aspects that are important to understand is that ABB, and also I think this is true for most of the larger OT companies like Bosch and Siemens and others, we typically have a very wide range of products. So we sell motors, we sell solutions for factory automation, smart buildings, we have marine applications, we have robots, etc., etc. And on top of that, we obviously we have then also a lot of software services that we also provide to our customers. What we want to do now is obviously we always want to make our products more capable, adding more functionality to them. And this is what you see here on the right-hand side of the screen. So we want to add things like AI, we want to add things like analytics, we want to add more advanced remote services, etc. And basically all of these functions requires connectivity. Now, many of the products that we have today, they already have connectivity. Some don't, but many of them do. But there might be the case where we want to have a different type of connectivity that we do not have today. We might want it to be more cloud native, for example. We might have remote services today that are sort of collecting statistical data for analytics, but in the future we want to do much more advanced remote services, VR based or etc. So connectivity and having a high performance and high reliable connectivity is important for our products going forward. Another aspect that's important is that we sell our products on a global market, and obviously we want to have seamless connectivity all over the world. So in order to achieve this, we want to have standardized communication, and that's why work that is going on in for example 3GPP is so important, and that's why I think there is a very good connection between sort of the presentation that I'm now presenting and the presentation that Krister will give later on in this webinar. So we want standardized connectivity that we can use globally. And once we have that, of course, we also need the business-to-business solution to run on top of this. So that's important. Another aspect that we get if we have connectivity is that we get freedom to deploy software functionality. So this is true for us as a vendor, and it's also true for the end customer. So if we have high performance connectivity, we can choose whether or not we deploy the software embedded on the device, or if we do it on premise or regional or in a data center, for example. And typically what happens is if you move to the right of this picture, you reduce the cost. You reduce the cost of deployment and you reduce the cost of maintenance. But you also increase the requirements on for example, latency and security, etc. So that's why that's another aspect why this high performance connectivity is important for our applications. So looking into our applications then and what we see 5G can bring, and I'll show you this picture, and I think you've seen this one before or a version of it. So these are the three legs that 5G stands on, with the enhanced mobile broadband on the top, and then you have the massive machine type communication, and then the ultra reliable low latency communication. And I think the enhanced mobile broadband, we will surely use it in industry, but I think the other two are more important for our industrial applications. So the MMTC and the URLLC communication. Some of these features are available in current release 15. But I think that more and more of these functionalities will become available in future releases, so release 16 and 17. And I know Krister will talk more about this. So I am expecting a sort of a larger industry adoption once release 16 and 17 becomes available, and we have chipsets and modules to use. So what will we then use these enhanced features for? So to the left, I mean, we have the performance boost. That's quite obvious that we will get better performance than what we have with LTE, and that is nice. But I think what's even more important for us is what you see in the middle of the picture here. So that's being able to run predictable services. I think that's key in a lot of the industrial applications that we foresee, and for sure also in smart manufacturing. On the slide here, it's that states network slicing as one example, but there are of course different mechanisms to get a better and more predictable service. And I think Krister will touch upon a couple of these. And once we have these predictable services, we want to move to the right side of the picture, which is to scale this. And scaling is not only having an increased number of UEs, but also to scale or to integrate or fit this into a wired network as well. So we see a quite close connection between 5G and TSN. And what we want to achieve is basically to have one universal connectivity or a converged factory network where 5G and TSN have the same look and feel for the user, and you just use the wireless technology where it's more appropriate, and use the wired technology where that is a better fit.
Krister, a short question from the chat. What is TSN is the question.
Well, the acronym stands for time sensitive networks. So it's basically, I'm not a super expert, but it's an evolution of Ethernet, where you can run communication more deterministic than you can do today. So let's then dig a little deeper into the factory case or the factory applications. And to the left here, we have some of the let's call it customer trends. that are sort of impacting the automation or impacting how we think manufacturing will need to adopt. We see that there will be a higher level of individualization. So products will be tailored more and more tailored to the consumer or the region or the country. We experience more volatile demand. And as a result of that, we also see that product life cycles becomes shorter. So what does this then imply? Well, obviously, with automation, you want to improve productivity and efficiency. That's clear. It's always been the case. But I think the key thing here is what is highlighted in that red box, so flexibility. So we need to improve the flexibility in manufacturing. You want to be able to ramp up quickly as the product life cycles become shorter. You want to reconfigure and rescale and ramp up quickly when needed. And you also want to sort of automate more and automate easier. And then at obviously the goal, the long end goal will be to have an autonomy. But I think where 5G can make a great difference is when it comes to flexibility. And that can mean different things in different settings. So it could be that it's easier to install a wireless sensor and get new measurement data. It could mean that you have high performance wireless that allows you to run AGVs instead of having conveyor belts. It could be that you have mobile robots that are capable of doing different tasks in a factory, so that you can change your production more quickly and easily than you can today. So if you look at sort of the vision for a smart factory of the future, we think that it needs to be a lot more adaptive. It needs to be able to meet the needs that we've discussed and that we've listed here on the left-hand side. We think that key in order to make this happen is to have this converged factory network where wireless where you have a wireless and wired network with the same sort of look and feel, that you're then able to run predictable service with high quality over. And I think a key to this, in order to make this happen, is if we have standardized solutions. So working through 3GPP, working through 5G ACIA and other bodies in order to push the technology in the right direction. And also projects like this then is a perfect way for IT and OT companies to come together and take on these challenges together. Yeah, that was my last slide, Leefke. I don't know if there are any more questions.
Not on the chat, but if there is anyone who would like to ask a question now, it's a good time to do so before we hand over to Christian. Otherwise, I guess we will move on to Christian and then take all questions at the end.
Sorry, Leefke, can I? This is Hans Bergström. Just a question,
absolutely.
and I'm not sure you can answer, Krister, but I'm just curious to see, is there? I mean, what is the timing aspects of all of these for ABB? Introducing things into the factory, and I know, of course, certain things are already there, but I'm I'm interested, you know, from a 4G, 5G, 3GPP kind of perspective.
So some things are already in place, but I would still claim that a lot of it is still on sort of a trial level. We install technology and we perform different trials to evaluate it and see what it is and how well it performs. So I think before we see sort of a more broad uptake, that's probably a couple of years into the future. And also, as I mentioned, I think that some of the features that I believe are coming in release 16 and 17 will also boost the interest for the technology.
All right, thanks.
No other questions? Then Christian, you can go ahead.
Okay, so I grabbed the screen. I hope you can hear me okay and see my slides.
Yes, works fine.
Okay, very good. Then also a warm welcome from myself. As Leefke said, my name is Krister Hoymann. I'm with Ericsson Research, located in Germany. There I'm heading the 3GPP RAN delegation. So I'm attending RAN plenaries, and I'm then, like in that role, responsible for the radio standardization within Ericsson. And I'm delighted to tell you about what 3GPP RAN and probably also a little bit of the core network side of 3GPP has done for 5G in manufacturing environments. I will at the beginning go a little bit into the history of how 5G started and what we've done within the releases that are done, so release 15 and 16. And then I will go a bit into the future, tell you in more detail what release 17 is about. And then I will highlight at the end the main themes for manufacturing, because you know 3GPP RAN is of course working on many use cases, but I have 3 examples where we explicitly evolved the system for manufacturing, and there I will go into a bit more details. That will be the outline of my talk. So, starting with the history. So this is a, before I start, I have to apologize. I realized I have a lot of abbreviations, and I already noted some might be difficult for people not into the matter. So if I use any abbreviations that you're not familiar with, please shoot and interrupt me. I'm happy to explain it. The slides will have a page with abbreviations in the end, so if you want to have a look afterwards, they will be all listed. Okay, IMT and 3GPP RAN timeline. So first of all, please focus on the upper part of that picture. That tells you the IMT 2020 timeline. And IMT 2020 is basically the process that the ITU has set up. And the ITU is a subgroup of the United Nations, which is responsible for a globally harmonized spectrum allocation. And these are the guys that usually start or trigger the creation of a new generation. Usually it works that they have a bunch of spectrum that they want to globally harmonize. And then they set up a process which is usually composed of an initial phase where requirements are collected. Then there's a proposal phase where any standards organization can input candidate systems that are expected to meet the requirements. And then ITU goes forward to evaluate all the proposals, and whatever proposal has met the requirements is then kind of specified as the IMT 2020 system. And IMT 2020 is kind of the acronym, or has the meaning of 5G. You probably remember 4G was IMT Advanced. 4G was IMT Advanced. The 3G was IMT 2000. So this is the process that the ITU is setting up. And then at the bottom now, the white boxes, you see the 3GPP timeline. So basically back in 2015, we started with an initial study item on channel models, but soon we went forward into a study item on requirements. So we kind of matched the IMT phases. And then, having done the requirements work, we went into the so-called NR study item, and NR is the acronym for the new radio, which is kind of the name of the 5th generation radio access network. So we had a study item, and you can imagine a study item in 3GPP is a little bit like a research project where different solutions are being studied and evaluated. And going forward from the study item into the work item phase, then the most promising solutions are being selected, and those are then standardized. So in the end of the work item, we usually have the specifications written down for the features that have been selected to be standardized. And then you can see release 15 was then the first release where NR was standardized. And it had a little bit of a staggered ending because we had different flavors of NR completed at a different point in time, but roughly it was 2018 where the first version was completed. Then release 16 was basically the first release after the go to live, basically, so the first evolution of NR. We completed that in June this year, and now, as you can see from this orange bar here, we are now in release 17, so the second enhancement step of NR. So this is basically where we are, but going back to the requirement phase, the requirements have been derived from use cases which have been identified to be important in the time frame of 5G. And here you can see the 4 use cases that had been prioritized. And of course, you can see at the bottom left, mobile broadband use cases, so the traditional smartphone use cases, was of course one of the use cases that 3GPP and also the ITU was looking into. Then if you take a smartphone and don't give it into the hand of a human, but glue it kind of to the outside of your house or to the outside of your office, then we talk about fixed wireless access, so a kind of a wireless replacement of a fixed access to your house or enterprise or office. Anyway, both of them have very similar kind of requirements. It's basically internet traffic, video streaming, voice. But then on the top you see the 2 other prominent use cases, or I would say use case families, and that is basically both in the area of machine type communication, or MTC as we call it. And as that use case families was so broad, we split it up into the massive machine type communication use case family, and then the critical machine type communication use case family. And I guess you know probably better than me that, I mean, these MMTC use cases are characterized like being very delay tolerant, being very low in data rates. And it's basically about this smart meter application. So we have smart meters which send their number, so a couple of bytes every minute, every hour, maybe only once a day. So they are not very demanding, but we expect them to be very high in number. So, and then if you take all of the smart meters in conjunction, they can generate quite an amount of traffic as well. On the other hand, then is the critical machine type communication, and I think here you can see the manufacturing use case explicitly. But these are use cases which have in common that they are very time critical. They rely on very robust and reliable transmissions. So they are kind of mission critical use case families. So these were the 4 use case families where the foundation of 5G was built from the start. So you can see that, I mean, although I will explain that we did enhancements in release 15 and in release 16 and 17, this should illustrate that already the first drop of NR, so release 15, was based, or the basic design principles of NR was based on these use cases. Came out of it basically. So what was the outcome from a technical perspective in release 15, so the first drop of NR? And here I list, I would say, the 4 technical highlights from my perspective that really are unique, that differentiates NR from previous systems. So starting from the left, multi-connectivity was one cornerstone of the design, of course driven by the desire to reuse the investments that the mobile network operators have done already in spectrum, in sites, and in coverage. So we wanted to leverage all of those investments also for 5G. And it means that you can basically connect to 2 sites or 2 base stations, to 2 systems even. So you can be connected to a 3G system or to a 4G system, and then at the same time being connected to a 5G system. Or you can be connected to one site, but then another site helps out either with a data transmission or with a control plane transmission. And the benefit of that is, of course, that you can increase data rates as well as reliability, depending on what you are transmitting. Then the second group here is relating to the, I would say, the fundamental waveform. So the fundamental shape of the electromagnetic wave that is like traveling through the air. And normally we've kind of changed with every generation. We've changed the waveform, but not going from 4G to 5G. So we kept OFDM as the basic waveform. But what we changed was we changed the numerology, or we made it flexible. So in LTE we had OFDM, but we had a fixed numerology. That means the subcarrier spacing, so the way how you set up the spectrum had a fixed separation into subcarriers, and meaning in relation it had a fixed duration in time of the smallest time unit, an OFDM symbol. But for 5G this is flexible. So you can set up a system with a very small subcarrier spacing, depicted in this picture, leading to a bit longer OFDM symbol, or you can have a wider subcarrier spacing, leading to a shorter OFDM symbol. And the consequence of this flexibility is that we can optimize the 5G system for various deployments. So we can have an optimum numerology for, let's say, macro outdoor networks, where the cells are pretty large, where multipath propagation can be quite huge, but we can also optimize it for, let's say, small cell deployments and even indoor deployments. Then it has the advantage that you can optimize for different frequency bands, because we had the situation with 5G that the spectrum that we were targeting was not a single band like in the generations before, or not even a single frequency range, but it was a very wide range, going all the way from 700 or 600 megahertz at the bottom, all the way to tens of gigahertz. So I think formally it goes up to 100 gigahertz. So this flexible numerology allows us to have an optimum configuration for low bands, as well as for mid bands, as well as for the high bands. And it allows us to have a very wide bandwidth. So again, on the low bands, the spectrum is quite good when it comes to propagation conditions, but it's very scarce, I would say. So the bandwidth that each operator gets, or every user of a system gets, is quite small. But up in the mid bands or in the high bands, we have pretty wide bandwidth. And this numerology allows us to address this wide band. But as I explained, the relation between the subcarrier spacing and the OFDM duration allows us as well to go to a lower latency. So by increasing the subcarrier spacing, we reduce the OFDM symbol, and that inherently makes the system faster. Then 5G and the core network side is very often determined as the cloud native core network. And I would say for the radio, then I would say it's a MIMO native design, because we've really designed from the very beginning the system to be based on massive MIMO. So it can from the very start handle a lot of antennas. Of course, it's difficult in the low bands to have many antennas, but if you go up in the frequency domain, you know that antennas becoming smaller because they are usually half a wavelength long. So the higher the frequency, the smaller is the antennas. So the more antennas you can put either at the base station or at the terminal, and that allows us either to gain coverage. So by beamforming, you can increase the range of the transmission. You can increase data rates. So by having multiple transmission to the same receiver, you can increase the data rate, as well as you can have multiple simultaneous transmissions just separated by the antenna, and that increases the capacity. But the MIMO framework, as well as you can think of, one part of this is a little bit like the physical layer connectivity. So you can think of a MIMO system with multiple antennas, and then you tear the one group of antenna away from the other group of antenna, and you can think of two kind of transmit-receive points, both transmitting to the UE. So you can have the same kind of benefits as with the regular multi-connectivity of carrier aggregation or dual connectivity, just on physical layer. And that is an interesting kind of use case, which also gives you higher reliability. So it's very, very well applicable to the smart manufacturing use case. Then last but not least, there was a focus on the lean design. And that is a bit depicted in the picture down here, where at the top you can see the signals that an LTE base station has to transmit, even in the middle of the night when there's no traffic whatsoever. And you can see here that there's a bunch of broadcast signals, there's a bunch of full band control channels, and there's a lot of reference signals that have to be transmitted 24/7, and those do not scale with the load. But NR has been more designed according to the lower picture here. So if there's no traffic, then an NR base station is basically silent. And only when there's data to transmit, then of course you have to fire up all the reference signals or the control channels, of course. Then it would look different, but in terms of low load, and there's hardly any transmission to make. And that allows us to be very energy efficient. Of course, it's spectrally efficient because you don't disturb your neighbor. I mean, just imagine you are a neighbor of such an LTE base station. I mean, the guy or the cell is very empty, but still it transmits a lot of interference to you. Then it allows to do spectrum sharing, and that is one of the concepts that you can start an NR operation on the exact same carrier where an LTE operation is already taking place. So within the empty spaces here in the bottom picture, you can actually operate an LTE network. So we can share LTE and NR on the exact same carrier. And finally, it's very future-proof, because whatever you can come up with in release 18, 19 or whatever, we can kind of design it here into the empty spaces. While in LTE, it was a bit difficult to design new things because it always had to be designed across or around the signals that needed to be transmitted. Okay, so that is the fundamental of the first release, release 15. Then what did we do in release 16? And here I just group the work items that have been conducted in release 16, and I group them again according to the use case families that you saw at the very beginning. So on the left-hand side, these are work items that we did primarily targeting mobile broadband use cases. Then in the middle are use cases primarily targeting critical MTC use cases, and then on the right-hand side, the massive MTC use cases. And I mean, just from a, let's say, helicopter perspective, you can see that, I mean, 3GPP did quite a bit on these new use cases for critical machine type communication. I mean, of course, for mobile broadband, we did enhancements to MIMO, we looked at the power saving, we had enhancements for carrier aggregation and dual connectivity. But then on for the use case families of ULLC, we enabled 5G to not only operate on licensed spectrum, but also on unlicensed spectrum. And here, 3GPP had just finalized an operation both in the 5 gigahertz unlicensed as well as in the 6 gigahertz unlicensed space. And it can be standalone as well as license assisted. So a 5G system of release 16 can operate solely on the unlicensed, or it can be a combination of a licensed with an unlicensed. Then we added support for private networks, and probably, yeah, most interesting, maybe you don't see it that much. I mean, 3 of these items I used a blue font instead of a black font, and these are the items where I will go deeper into towards the end of my talk. So positioning, and then the enhancements for ULLC on the physical layer as well as industrial IoT. I have a more deep dive later. And besides that, release 16 contains V2X, or vehicle to everything, which contained basically a side link. So usually we have the downlink, which is the connection from the base station downwards to a UE, and then the uplink whenever UE wants to connect to a base station. And the side link we refer to then when a device is talking to a device directly. And the first use case for that one was the automotive use case, where then a vehicle talks to a vehicle. And that can be done either direct or via the infrastructure or via the networks. That's why we call it V2X. Then, yeah, last, I mean, just to complete the massive MTC use cases in release 16 were still handled by the LTE side of 3GPP systems. So the LTEM and the NB-IoT were enhanced there. But in release 16, we didn't see any enhancements of NR going into this low cost and low power segment. But that changed in release 17. You will see it soon. So, but before we go to release 17, back to the timeline. So the left part of the timeline should be familiar with you. And now we've entered release 17. And as you can see again from the orange bar, we are at the end of Q3 2020. So we've just started release 17. And due to the corona pandemic, 3GPP has transformed all the physical meetings into electronic meetings. Yeah, giving us a little bit of a headache because we need to adapt our ways of working to these electronic means. But I think after a little bit of a bumpy start, I think it's going okay. But there is, of course, a consequence that electronic meetings are not as efficient as face-to-face meetings. So there will be a consequence on the end date of release 17. Today, the end date is set to September 2021. But in the last week's round plenary, we have already said there's an anticipated delay because of the electronic meetings of another 6 months. So, and I think that is the kind of the expectation of everyone in 3GPP, that we will see a further delay of release 17 by 6 months. That will mean we will end very likely release 17 by March 2022. That is what we call then the functional freeze of release 17. It is not yet agreed. We will only decide it in December this year, but I think a 6 month is the best guess that we can have. Okay, so what's in release 17 then? And again, I have now 2 slides with the content of release 17. The first slide lists all the enhancements, so things that were already in 3GPP that we are going to enhance. The second slide is then listing new stuff, so things that we added on top. And again, I tried to group the work items according to the main use case families that they are addressing. And again, you can see a number of items are primarily addressing mobile broadband use cases. Then in the middle again, you see items addressing ULLC use cases. And then at the bottom, you see MMTC use cases. And again, it's the usual suspects. So we look into power saving. MIMO is always a topic. We are further evolving what we call integrated access backhaul, or IAB, and that's the 3GPP term in 5G for relays. So if you introduce an intermediate node between a base station and the UE that is forwarding data back and forth, and in 5G we call it IAB, and we are going to enhance that one as well. And again, we have enhancements item particularly for ULLC or IoT use cases, as well as we are evolving further the positioning. And as said, I will come to these in more details. So what was the new functionality in release 17 then? Again, same grouping. The top one goes for mobile broadband, in the middle then for ULLC. And here you can see that 3GPP has started a study item on XR. And XR is the term for augmented reality, virtual reality, and mixed reality. So these kind of new use cases that you can see also on the right-hand side here. And we expect that it has a unique traffic pattern, and it has quite excessive requirements on the network. So we're starting a study item here to look what can be potentially enhanced. And at the bottom here, probably worth noting is that on the MMTC side, in release 17, we will see the first move of NR into the use case families of massive MTC. So we have a study item and likely a work item to reduce the complexity of NR devices. Because, I mean, NR devices, as you know, I mean, they are pretty powerful. But for the MMTC use cases, it's not always needed that you support gigabits per second data rates or that you support megahertz of bandwidth. So here we look into how you can reduce the complexity, and I will come to that in a minute. Okay. Now, what exactly have we then done in the IoT and URLC space? So far, I've looked into what 3GPP has done overall, including all the use cases. But this is now particularly for the URLC use cases. And I said from release 15 onwards, I mean, the initial design was based on the flexible OFDM. So we have mini slots, which is a name for very short time periods, and we have this flexible numerology. And of course, we added very robust modulation and coding schemes. So when the signal quality is bad, we can add a lot of redundancy and make the transmission robust. And with this flexible numerology, I said we can push the time dimension to very short time units, and that allows us to have very fast repetition schemes. So HART is our term for a retransmission protocol. So whenever you transmit a packet and it was not correctly received, the receiver can ask for a retransmission, and that we call HARC or ARQ mechanisms. And the faster you can request a retransmission, the better it is from a latency perspective, and then of course from a reliability perspective as well, because in a given time duration you can have many more retransmissions, making your transmission much more reliable. Then PDCP duplication, that basically relates to this multi-connectivity. So you can duplicate your packet over multiple base stations, or even over multiple base stations, such that it is kind of transmitted over two legs. So it can come from the left-hand base station as well as from the right-hand base station. And whenever the left-hand base station has an issue, it still comes from the right-hand side. So it's very much for robustness. Then we added features called semi-persistent scheduling in downlink and configured grounds in uplink. And that is very much a scheduling feature to allow very deterministic way of data transmission. Because traditionally in cellular systems, we have a dynamic scheduling. So whenever data arrives in the buffer, we use as many resources as available to transmit that buffer, and then we try to empty that buffer. But then in this context, it was highlighted that we need very deterministic and very short latency. So here, so semi-persistent scheduling and configured grounds is a way of kind of pre-allocating resources both in uplink and in downlink, because we know that the packets will come. I mean, we know in advance for certain application it will come every 20 milliseconds or every 100 milliseconds. So we can pre-allocate radio resources every 50 or 100 or whatever milliseconds, such that whenever it arrives, we can directly transmit it up or downwards. And then the last 2 points are related to kind of internal quality of service management. So logical channel restriction means that now we can kind of create multiple logical channels in the UE, and we can associate them to quality of service frameworks. So we can open 2 connections, basically, one for mobile broadband and the other one for critical services. And then we can tell the UE basically if they get a resource allocation in uplink, for instance, whether this is a very robust resource allocation with a lot of redundancy, or whether it's more of a best effort allocation. And then the UE should either send an internet packet or an industrial robot command. So that was what we did in more detail in release 15. Then going to release 16, basically we enhanced the upper 2 points are basically control channel enhancements to make it, to make the downlink control information smaller and more configurable. And smaller always means it's more robust, because you can, you don't need to transmit so many bits, and then each bit that you send is more robust. PDCCH monitoring makes it more, reduces the latency, because it was a feature to send control channels much quicker. The 2 next areas are basically uplink enhancements. So where you can repeat uplink transmissions. So instead of sending it once and wait for the retransmissions, you can transmit your uplink data 3 times, 4 times, 16 times, really making it more robust. And we improved or enhanced the error recovery schemes to make that more fast as well. The next two guys are then related to quality of service as well. So we had an intra-UE prioritization. So when the UE is getting 2 grounds, so it gets resources for 2 types of traffic, then we have now rules in place that it can basically prioritize the ULLC data over the mobile broadband use case or the mobile broadband data. So it would basically drop the low priority packets. And it can even preempt in uplink. So in an inter-UE case, so in case a base station has already scheduled a mobile broadband UE, it can stop that transmission because there's an urgent ULLC transmission coming in. So you can stop an ongoing transmission and then ask a more high priority UE to go in and transmit. Yeah, then we had enhancements to this SPS and configured grant configuration. So basically making it even more fast. So I think in release 15 we were able to allocate up to 10 millisecond periodicity, and I think from release 16 I think it can go down to half a millisecond configuration periodicity. Then we introduced the time sync protocol, and that relates back to this TSN network that Krister already mentioned. This time-sensitive networking, which is a kind of from a 3GPP RAN perspective, an application protocol allowing to time synchronize the applications on both sides, so the server with the client. And in order to support that, we introduced a time synchronization scheme between the base station and the UE, because that is kind of the fundament that the base station and the UE are in sync, and they know about the absolute time, such that they can put timestamps in the ingress points and the egress point of the 2GPP systems, such that the TSN networks on top know how long it took to for a packet to traverse the 5G system. Then the multi-connectivity, we extended from 2 legs to 3 and 4 legs. We looked into header compression. Up to now, we only had IP header compression. So an IP header coming in, we could compress. But in release 16, we added Ethernet header compression. Also, because this TSN network is an Ethernet-based standard. So we wanted to have a very efficient transmission of these packets as well. And then outside of the ULLC and IoT work items, there were 2 more features relevant for the smart manufacturing use case. And one came from the mobility work item, where we specified a make before break handover. And you can think of it like a multi-connectivity. So when you come close to a cell border, you create a connection to the target cell before you stop or before you break the ongoing connection to the source cell. So once you cross the border, basically you are connected to the source cell as well as to the target cell. And only when you arrive safely into the coverage of the target cell, then you stop the transmission to the source cell. So that is a means to have a very robust handover. And then in the MIMO work item, I already said there's a MIMO feature called multi-TRP, multi-transmission and reception point. So basically that you are connected to 2 antenna points or 2 antenna panels at the same time. And that is also usable for increasing robustness, because you can transmit the same packet then from 2 angles. Then in release 17, what are we doing now? Basically, we are enhancing the feedback. So both the channel measurements we are trying to enrich so that you have a better understanding how the channel looks like. We are trying to enrich the HARC feedback, so the information that is needed to retransmit an erroneous packet. Then we look further into this intra-UE multiplexing. So if it gets 2 grounds, one for a high priority transmission, one for a low priority transmission, what can the UE do? And in release 16, it's just dropping one but transmitting the other. And then in release 17, we look how it can be multiplexed. So probably without dropping one, you can probably multiplex both. And then we look into unlicensed as well, and look what features has been done for unlicensed, and some of them are potentially useful for URLC use cases as well. And we're enhancing further this time synchronization. Yeah, last but not least, then we look into further quality of assistant or quality of service assistant information, and here it's this survival time that is added on top of the usual quality of service KPIs that are aware, or that the network is made aware of. And finally, again from the MIMO work item, as I said, this multi-tier P in release 16 was standardized for the PDSCH, which is the downlink data channel. And in release 17, we look at the other channels. So for the uplink data channel, as well as for the control channels, to be able to transmit those from multiple points as well, so that we can use this reliability tool also for the other channels. Okay, so that was a deep dive into the particular area of IIoT URLC on the radio side. And now I come to the core network side, a little bit outside RAN, but I think it's anyway interesting for this audience here. So what was done on that front? Basically, what was added in release 16 to the 5G core network, or to the overall system architecture, was a high reliability feature by adding a redundant user plane. So basically, you can have a separate PDN connection, either via two completely different terminals, having two different SIM cards even, or over these multi-connectivity solutions of dual connectivity and carrier aggregation. Then we added the corresponding quality of service monitoring. In the core network, we also added support for private networks or non-public networks. Then they finalized the support for Ethernet, so 5G LAN services. Because as I said, I mean, up to now, the cellular systems was basically addressing IP-based applications, but now we completed the support for Ethernet-based application, and they kind of finalized the support for this time-sensitive communication, which is kind of, I understood this as a superset of time-sensitive networking. And it had three components: the QoS flows, so how to associate then the time-sensitive communication quality of service flows to the cellular quality of service concepts and flows that we had. The integration of the 5G system into this TSN, because then from a TSN perspective, the 5G system ends up as a TSN bridge. So it's basically seen as a bridge or a switch with an ingress point and an egress point. And yeah, from a TSN perspective, it doesn't matter whether it's a 5G system or whether it's a cable. It just sees a connection between two endpoints. And then we added this time synchronization protocol, basically giving every packet that comes into the 5G system a timestamp, and every packet that leaves the 5G system then a timestamp again, such that then the overarching TSN network can reduce this local time and then kind of recalculate the overall TSN time for that. That was part of release 16. Then in release 17, it's been working on the time synchronization again, and in 15 and 16 it was only possible to have the master clock in the network as such, so at the base station or in the core network. But we are now adding support for having that grandmaster clock also at some location together with the UE. And there's one enhancement such that two UEs which are in the same cell, you don't need to go all the way through the core network to have a communication from that one UE to the other UE, but you can have a kind of a shortcut via the UPF, the user plane function. So it's a little bit of a latency reduction feature, maybe even reliability reduction, reliability increase, so that two UEs within the same cell can talk to each other more quickly. And finally, as I said, we are exposing the capabilities of the 5G system to the TSC network, basically to this TSC controller, such that then the overarching application can configure the system accordingly, because the TSC controller needs to make sure that all parts of the TSC network are then configured correctly, and 5G will be then one part of it next to others. And this exposure of the network capabilities is done in release 17. Okay, two more functionalities a bit in depth. Positioning. In release 15, we added positioning, but not really from an NR perspective. So release 15 was basically an LTE-based positioning. So you were configuring gaps for the UE to kind of tune away from NR, listen to LTE positioning, and then come back and tell NR what the position was. And of course, it supported GPS-based positioning, as well as this assisted GPS positioning. So where you have reference stations that are correcting or that are allowing to correct the GPS position. And with this GNSS RTK, you can, if I understood correctly, go down to a decimeter or even a centimeter level positioning outdoors, assuming you have a good coverage to satellites. And then, I mean, all other means of positioning, you can sense Bluetooth devices, you can report on Wi-Fi access points, you can report on barometric pressure. All that was possible to report back to a positioning server, such that the positioning server then can give you an accurate positioning. But in release 16, then we added really the, I would say, NR foundation. So we added a wideband positioning signal to NR as such. And the motivation was both regulatory as well commercial use cases. And the regulatory use cases, these are basically first responders, so public safety communities, policemen, firefighters. But the commercial requirements, they basically came from the smart manufacturing use cases. But in release 16, we tried to address both. And the outcome was that we have a wideband signal, basically uplink and downlink, where the UEs can measure on. And by that, we can kind of implement various positioning tools. So we can have a time difference of arrival or RTT-based measurements, which allows you to do triangulation. So as soon as you receive a positioning reference signal from 3 different points, then you can calculate by triangulation your position. You can spice that up with angle of arrival or angle of departure based positioning by using the beamforming tools that we have. So if you're pointing to the right-hand side, then you know, if you're pointing your beam to the right-hand side, you know, obviously the device is somewhere positioned on the right-hand side. Or if you receive from someone over a beam pointing to the left, then of course, you know, this guy is obviously on the left-hand side. And in release 16, I mean, with these tools that we have standardized, we are basically meeting both the commercial as well as the regulatory requirements, which basically boils down to a below 3 meter accuracy, horizontal and vertically, indoors as well as outdoors. And now I'm wondering if that is a meter or a centimeter. I will have to check that. So then, in release 17, as you saw, in release 16 is for positioning the baseline. In release 17, we're enhancing it. Here, the requirements are basically coming from commercial and even indoor industrial IoT use cases. So here we are targeting an accuracy below 20 centimeter, so 2 decimeter, and in addition, a very low latency. The evolution areas, I mean, how can you tighten the positioning? That's of course always a tricky question because we already have a wideband system, so you can't make it even more wideband, so that you can't do. But you can look into interference mitigation. So you can try to mute your neighbor cells such that the reception of the positioning reference signals becomes of a better quality. Or you can give more enriched feedback. So you can tell the positioning server whether you've received the positioning reference signals in a line of sight or a non-line of sight matter. Because I mean, if you do triangulation, it really matters whether it was a reflection or whether it was the direct path. Or you can tighten the UE requirements basically, so you can push the UEs to have a more accurate measurements. So these are the, I would say, main tools in release 17 to improve the accuracy. And finally, we are looking into integrity protection. So whatever you send to some kind of positioning server or whatever you receive from as assistance information should be integrity protected. Okay, last but not least, as I said, in the MMTC space, we are looking in release 17 into these reduced capability devices. So it's I would say the first time we are going into that segment, but still I think the very low end of this MMTC segment is still addressed by the current systems of NB-IoT and LTM. I think if you look at the device cost for which you can buy an NB-IoT or an LTM chip today, that is more in a single-digit dollar range. So you can get it for $4, $5. You can get such a chip. I don't think we will get there with release 17 NR, but still we are trying to push down the price tag of NR regardless. The main use cases here are wearables, industrial sensors, and video surveillance cameras. So wearables, I mean, it's clear, I guess the Apple Watch and the Google Watch and whatever smart watches out there. Industrial wireless sensors is then, I mean, very much relating to smart manufacturing use cases. So every kind of sensors in industrial environments, not so reliable, or hungry, or not so time critical, but yeah, is still needing to send data in a 5G system. That is a target use case here. And last but not least, then video cameras. They're also in between. I mean, not so data hungry as some other 5G use cases, not so critical from a time perspective. And what are we looking into? Basically, we are looking into UE complexity reduction. So we are looking to reduce the UE bandwidth from, as I said, several hundreds of megahertz down to orders of 20 megahertz, so like a UE, an LTE type of bandwidth. And we are reducing the number of receive antennas, basically. So we are looking, instead of a UE mandating to have 4 receive antennas, we look into 2 or maybe only a single receive antenna. We look at half duplex schemes such that the duplex filter can be taken away from the UE. And then we look into relaxation when it comes to throughput or time requirements. Then on the power consumption, we're looking into an extended DRX scheme. DRX stands for discontinuous reception. So basically, it's a UE sleep mode. So you tell the UE, okay, there will be no data for you within the next, I don't know, 200 milliseconds. The UE goes to sleep and wakes up afterwards, and then it's reachable again. And by extending these sleep periods, you can save UE power. And finally, I mean, by reducing the complexity, some of these tools will hit back on coverage. I mean, for instance, if you take away receive antennas, the signal quality at the receiver side will get worse, which is immediately hammering on the coverage. And here we are trying to compensate for the potential coverage reduction due to this complexity reduction. So here I think we talk about a couple of dB that we are losing, but we want to kind of get that back potentially through repetitions. Okay, I think that is the last slide, if I'm not mistaken. Yes. So yeah, as I said, I told you a little bit about the history of 3GPP and what we've done in release 15, 16, and what we are currently working on in release 17. And now I see Leefke.
Yes.
Back to you. Thank you.
Thank you very much, Christian, and also thank you very much to Krister for the good presentation. So